Yeah, this is designed to be not a hard one, but just a quick kind of stuff, right? So this first question you saw it in the lecture 1, right? So what is the answer? How many of you said 3.2, and how many of you said 2.2? The dual core or single core? Hope you didn't say it depends, because obviously it depends, right? How many of you said 3.2? How many of you said 2.2? Why? The answer, I think, is both are right? It depends on why you decide to go with one. So why did you guys choose? Why did you like 2.2?
I picked 2.2 because it's dual core, and that gives you the ability to handle more than one process at once. I mean, having more processing power is great and all, but if you only process one thing at a time, then it might not even all be used.
Yeah, so sort of that, right? I mean, 3.2, you get one thing going faster. 2.2, you get two of them, sort of slower. If you have a threaded program, then 2.2 could potentially be as fast as 4.4. I mean, if you sort of, right? Because you can use both of them at the same time. If you don't have a threaded program, you can run two processes rather than one process at the same time, right? On the other hand, if you have a non-threaded program which needs to go very fast, so some of you may do scientific computing or some of the other processing, and if you want one thing to go really, really fast and you couldn't make it into a multi-threaded solution, then the 3.2 would be good enough, right? So one of the ways you may tell your friend is to see if they can use both the processes, right? So if they have multi-threaded program, then 2.2 may work. But for example, if PowerPoint happens to be non-multi-threaded, so on the 2.2, you expect PowerPoint to be slightly slower, right? These machines are fast enough that it may not matter, but that's the trade-off you do, right? So there is no one answer depending on how you think about it. Either threads or multiple processes, you get the stuff. And the second one, it's sort of your homework project, but I sort of left it intentionally vague on what the amount of time is. How many of you said true? How many of you said false? True? Okay. What was the interpretation of time? Amount of time? Was it the wall clock time or the time it takes on the CPU? Or did you consider those? So when you think of the homework project, right, whatever operating system does, the amount of time it takes for your program to run, if you assume the amount, this is intentionally vague, right? So you would have to think about what it really means to say amount of time. The amount of time for your program to run on the CPU would be the same regardless of what the operating system does, right? Because if your program wants to compute pi to the 10th digit or something, and the computation takes 1 second, it will get one CPU. It has to take 1 second of CPU to do that task, right? Regardless of what you do, that should not change. What would change is how much time it perceives it to happen, right? So if you make the clock smaller or larger, then I may give you so little time. So I may give you 1 millisecond. So that 1 second, I have to give you over 1,000 intervals, or maybe 100 intervals or 10 intervals, and that may affect how long your program will take. So when you run the homework project 1 and you look at the time, right, you may see a slight variation when you change the hertz, which is essentially what we're asking here, right? But the amount of time your program itself would take will not change, right? So I'm not sure if you guys caught the different one. Hopefully for the homework project, you will look at that, right? So it's the amount of time. It's a wall clock time, not the processor time, right? But we'll look at the quiz on that. So on Wednesday you'll have the exam. I should be back. I'm supposed to fly in at 9. But I just don't trust the winter weather. So the TA will be here. I hope to be here slightly afterwards. You'll have 6 questions, sort of like this. I hope that you'll take half an hour, and then we can go over the answers right after the exam, unless I get stuck somewhere, right? I think Wednesday should be fine. The weather should be fine. So if there are any questions, concerns, yeah, I should be online, not probably during the daytime tomorrow, but otherwise I should be online somewhere, right? For the homework assignment, like some of you asked questions about the fork, what the answers and all those things. That's a good program for you to try it on the machines. I mean, this is not a very large program. You can try running those things. I strongly encourage you to try these things. Like when you talk about fork and threads and all those things, I encourage you to use one of those machines to try these things, right? And there's nothing like getting a feel of it on an actual machine, right? And like I said, by doing so, if you crash those machines, that's perfectly fine. As long as you don't physically do any harm, I'm okay, right? So are there any questions about what we covered so far? For the exam, you'll have whatever we covered till end of this lecture today, right? So we were looking at threads, right? So threads, as you may realize, at least from this homework project and everything, threads are very important as we go towards this world of multi-core, right? So regardless of so it's very important to understand what threads are and how things are. And you'll face the issue of threads, because the nice thing about threads are they let you share stuff across the same process, right? When you have 2 processes, they don't share anything unless you explicitly do something to make them share. And it's not that trivial, so you don't actually do it by accident. Whereas when you do threads, you can have multiple threads operating on the same program, affecting the way both of these things happen, right? So you can have one thread operating on some data without what we'll see in the next module, locking and all those things. So such that you can get twice the performance on a multi-core and all those things, but you can also shoot yourself in the foot very easily. And we'll see why it's important to worry about it, why threading programs are hard to debug, why threading programs are really hard to understand what's going on, because you have a lot of timing issues, right? So before we go in that, I just want to look at the different threading models, right? So one of the problems which affect here and also affects everywhere else is the more you have to ask operating system for something, the more time it takes, because the overhead of going from your process to the operating system and coming back, it always takes some amount of time, right? Maybe not too much, but even that little one is overhead. So you want to avoid going to the operating system as much as possible, and that's why you have buffered I/O. That's why you have printf and the scanf and all those routines, rather than doing read and write. And you do the same thing here. You would like to have a library where you deal with most of the stuff by yourself, right, at the application level, and you only ask the kernel once in a while, right? So that way you expected things to be faster. And the trade-off is now the operating system has no idea what you're doing, so it can do stuff which may or may not be good for you, right? And the last lecture, we left off with the notion of system calls. If you make a system call, and if it blocks, operating system has no way of knowing that you have other threads which could run, because it does not know about your threads, right? And that's the thing you worry about. So the way you map those could be in different models. One is a many-to-one, where you write the application library, which creates a notion of different threads, but it only uses one thread which is known to the kernel, right? So you get one thread from the kernel, and you make it look like you have multiple threads, right? It's good thing in the sense that you can use this model on an operating system which does not know about threads itself. You can run this on a machine where the kernel itself does not have a notion of threads. And so it's portable, and so that's one nice thing. And the problem is, if you block on any thread, so your library has to keep track of what each of the threads are doing. So it has to replicate what the operating system is doing without having all the capabilities, all the protections, all those things. If any of them does anything wrong, it's up to your library to deal with those. It can do a good job for the most part, but not always, right? So you can change that by either having many-to-many or one-to-one. In one-to-one, you get every user level thread maps into a kernel level thread. So the kernel knows all those threads, right? Which means that it can schedule them differently. So it can schedule each of the threads differently rather than your library and dealing with those. Or the other more realistic option is to have a many to many, right? So I can give you 4 application level threads, I get 2 kernel level threads, and a multiplex, right? And so those are different ways you can have this library built such that it sort of replicates what the operating system does. It does not have to go to the operating system all the time. And so you get performance and the flexibility, right? I think we have a, so traditionally systems let you do both. So you can have a library where some threads are directly mapped to user level threads, whereas few of them are multiplex, right? And you have more complex variations of doing this. And that's what most of the operating systems allow you, right? They let you either have one directly mapping or have something like this, right? Is there a reason why you don't want to have a lot of threads known to the operating system? Is there a reason why instead of doing 3 to 4, why wouldn't you want to have one-to-one mapping for everything, right? One of the problems I said was you have to do this from kernel to the application stuff. But the kernel could know all this, so it can actually do a good job. It can give you different stuff, right? Why wouldn't you want to reduce the amount of threads that the kernel would know? Which is also the same answer as why would you want to not have infinite processes in your machine? Yes?
Because of the overhead, handling all the threads would slow things down.
Yeah. So one of the overhead would be it has to keep track of all the stuff internally, right? So if you're thinking about processors, you have to have that many PCBs, right? That many process control blocks to take care of those. If you're talking about threads, if you create 1 million threads, right, the operating system has to keep track of 1 million thread entities, some data structure to keep track of those, right? And again, we don't want to do so much of those, so we try to push something off to the application, right? Because with the nice thing about application is, if your application which is asking too many threads, I can tell you don't ask too much, but I can still service somebody else. If it's an operating system, then any slowdown would kill everybody, right? So you want to avoid those, right? Right? Because the operating system manages everything. So if one of you is asking for too much stuff, I can say, I'm not going to give you more. I'm going to have a limit of, I can only give you 100 because that's all I can deal with. But if all of them push to the operating system, then it cannot do too much, right? But there are other issues that pop up just because these are threads and not processes, right? And the first one is the notion of fork, right? Fork is the call we kind of looked at for the homework assignment and the processes and stuff. Essentially, fork would create a clone exactly at that moment, right? Which means that all your variables are shared up to that point. All the contents go up to the point, right? Then we have to worry about what happens to the other resources, right? And we haven't looked at files and all those things. But when we look at files, you have to wonder what happens if you open a file and you do a fork. Do both of them get to write on the file, or only one of them get to write on the file, right? So that's something we'll worry about. We are worried about CPU resources here. So if you had many threads and you do a fork, do you create another process with that many threads? And what would the other threads do, right? Does that make sense? I'm going to try to use this one. So you have a, let's say you have an application, you create multiple threads, right? And this thread does a fork, right? In which case you expect that it'll create right? It'll have to clone everything. If it cloned everything, only this thread forked, right? These threads are doing something else. We don't know what these threads are doing, right? So what would, meaning like these threads, So what are these threads supposed to do? Does it make sense? You take the process up there. It has, let's say, 4 threads, right? One of the thread calls a fork, and the 3 of the other threads are doing X, right? We don't know what they are, because they are threads. They can do whatever they want, right? You do a fork. The fork semantics would say that you have to clone everything, right? So you have to create 2 copies of this stuff. So it's clear that this one did a fork. So you expect that, you can expect that this thread and this thread would kind of know what's going on. All these are original threads. If you were to clone these threads, what are they supposed to do, right? Because they never called the fork. They were doing something else. They were doing an X, right? So should these things also do an X, or should they do something else? Should they start over, or what have you? That's the challenge, right? Does that make sense? So when you do a fork in the threads, you mix them up, you have this soup of stuff. So once you go this way, so there's no clear answer, right? Can you think of how you would resolve this issue? Should you fork these threads? And if you do, what are these threads supposed to do? Yes. You can take a stab, because there's no clear answer, right? What could you make these threads do? Yes.
They could start at the beginning.
Yeah, they could start at the beginning, right? That's a understandable operation than start wherever they were, because no one knows wherever they are, right? The nature of the threads is nobody knows precisely what other threads are doing at the time, because they are just going their own business, right? You could start them from the beginning, right? But that may or may not be what you wanted, right? When you write a thread program, suddenly some thread did a fork, and now you have these clones which are redoing the whole thing again, and these clones have no idea that they were created because of a fork, right? And this could be a nightmare, right? Think about it. If you were to think about this as how would you write this program where somebody calls a fork and the entire system kind of messes up, right? One of the ways that you might have used a fork without you realizing is through a function call called system. How many of you used a system C call? So system, essentially you say system and you give a program name. So your system, you get system ls and it runs the program, right? Essentially system you'll do a fork and exec for you, right? You don't realize that you did a fork right there. So if you call system and you had a threaded program, you have this nightmare scenario where you suddenly created another clone where those threads had nothing to do with it. So it depends on how the mechanism wants to deal with that, right? So if you look at Unix, they have 2 different ways of forking. You have a way of forking where the fork will create another process with only one thread on the thread that created the stuff, so you kind of avoid those issues. You also have another specific version of fork which will fork the whole thing and create another threads which start running from where they are. So depending on how you do this, you have to be careful. So when you write a program with threads and you want to do fork, you have to deeply understand what's going to happen. Otherwise, you're going to have these threads which are being cloned, and they're going to start doing stuff which may not be what you expected, right? Yes? Oh, okay. There are other issues, right? The other issue is the notion of thread cancellation, right? When you have multiple threads, thread cancellation is the same as killing a thread, right? Which is the same as what you do in killing a process. So suppose you have, let's say you are using PowerPoint and PowerPoint seems like it's stuck, right? So you go into a task manager or something and you kill PowerPoint, right? That's you're essentially killing this process, you're canceling this process. And here the notion is something is wrong, you administratively go and without asking the process, you just kill it, right? And you expect that it'll clean up and go away, what have you. So when you're dealing with threads, right? Suppose you have 4 threads, and one of your threads decides that the other thread is not doing what it's supposed to do. It wants to kill it, right? The challenge here is you can't just kill the other thread because that thread may be operating on some data that is shared by both of you, right? So you remember the adder and subtractor, right? That thread may be in the middle of doing some things. So you can't just kill a thread because everybody's sharing all the contents. So in the notion of process, if the whole process is killed, everything gets cleaned up. So you don't have to worry about what they're doing because they're all going to be cleaned up and they're going to be cleaned up by the operating system. So you don't really care. You don't really care what files are halfway through and all those things because you're kind of okay, right? Because at the best, you'll corrupt the files, but at least the program will kind of end. Whereas here, you have other threads, you have no idea what they're doing. If you just kill them, that may mean that the whole program crashes because they may be operating on some data structure which destroys the whole thing. So you don't want to kill them. You want to, so depending on the way you do it, you can have a notion of asking politely, right? You can say, I want you dead. Whenever you get a chance, kill yourself, right? So what that means is when the thread executes, it keeps looking at this flag to say, am I supposed to exit? So when it's supposed to go through and then say, at some point it decides, okay, I'm in a safe state, now I can go check the flag. So it's up to the thread to decide when it can exit, right? So you basically say, I want you gone, and the thread, whenever it gets a chance, looks at the flag. And hopefully at that point, it's cleaned up all its data structures and says, okay, I'm going to cancel, right? So that's the notion, right? You never want to kill it immediately. You may say it asynchronously in some sense. You may have the system itself decide when is a good point to kill the thread, or you can let the thread decide when to go. But you never want to delete the thread without it knowing because of the shared notion of what they're doing, right? So when you write threaded programs, these are things you begin to worry that you didn't have to worry about before. When you write a program, saying things go wrong, you just kill it and you're fine. You cannot try to kill a thread unless things are all going fine because other threads may be operating on the same data. So you want everything to be in a safe state, right? The next issue is the notion of signals, right? Signal is the software notion of an interrupt, right? So essentially, that's a way for me to send a kill or some signal to the program, right? So many of you in Unix, if you do a Control-C, that's called an interrupt, right? Which is essentially you create an interrupt called sig interrupt, and give it to this. You signal this process, right? And typically, when you get a Control-C, the default action is your program will exit. But you can catch it in software and deal with that. How many of you programmed with signals in your C course? Or very few of you, right? Some of you that took networking class, right? You must have used signals when you're doing sockets and timers and stuff, right? When you're doing socket programming, network programming, you do an asynchronous program where you say, if any packet comes, let me know kind of stuff. I don't know if you used it, right? So if you use a select system call, you use select and timers, and when timer goes off, you get an interrupt, right? So essentially the idea here is you get an interrupt and you do something with it, right? So it could be stuff where the user gives controls or Control-C or things of that nature. It could be something generated by the program. So if you divide something by 0, right, your program may create a floating point exception, right? 1/0 is a floating point exception. Depending on the library you use, it may create a floating point exception, or it may create not a number or infinity or what have you, right? So there are many ways where your program creates this notion of a signal and tells you, right? And life was simple when you had only one thread, because when a process gets interrupted, it knows what to do. It knows either it should leave, or it knows it should clean up, or go ahead and do something. When you have multiple threads, right, the challenge is who's responsible for the system, right? Before there's only one thread, so it knew it had to take action. Here there are, let's say you have 10 threads, right? So when you get a signal, who should the signal go to, right? You would ideally want the signal to be delivered to the one which caused it, right? For example, if you did a floating point exception, that creates an exception, you want that particular thread to know that whatever math operation it did was wrong. So it divided by a 0. So you want to let the process know that it divided by 0 because the CPU is letting it know. And you want to give it to that thread, right? That seems like the logical thing you want to do. But you can't really do that if you have application level thread library, because the operating system knows that somebody in your process did divide by 0, right? That's all it knows. It does not know what thread is being manipulated, because it does not know who's actually doing the stuff. So it can deliver that to the application, but not necessarily to the exact thread, because no one knows what the thread is, right? So things of that nature become very complicated when you do a thread program. If any of your threads do something wrong, the operating system tells your process, one of you did something wrong. One of you did segmentation violation, right? Same as segmentation violation. If one of your thread does a segmentation violation, should you tell everybody, right? If you tell everybody, the other threads may have no idea what you're talking about, right? Because they're like, we are doing fine. We're not violating anything. We are operating within the parameters of what we're supposed to do. You're supposed to give it only to the thread that was creating this violation, except no one knows who they are, right? So you have many ways of dealing with those, right? It's very hard to do the stuff unless the kernel knows what the thread is. You try to give it to every thread in the process. That's one way of dealing with it. In which case, every one of your thread has to be able to deal with this stuff, right? So it may get a signal saying you caused a segmentation fault, and it may say, no, I didn't, right? Because it didn't create that, because somebody else did that. So all of your threads will have to deal with this on an individual basis. More common way of doing this is to have designate one thread which will deal with all segmentation fault, or one thread which will deal with all signals, right? Any which way you cut it, it's always much harder to program using threads than a process, right? You have multiple, you're creating as many threads. So you as application programmer has to know how many threads you created, what each thread are potentially doing. If one of them creates some sort of violation, you have to deal with those, right? Because if you don't, then your program would behave sort of strangely, right? And you'll realize it once you start writing in threads. So that's one of the reasons why writing in threads are not that trivial. That's one of the reasons why when you see multiple cores coming out, right, operating systems companies don't jump on the bandwagon immediately, right? Because they have to provide these system calls and libraries which are thread safe. And the application vendors like PowerPoint and all those things will have to make sure that their function would work on threads. It's not a simple notion of you put your PowerPoint on the new threaded machine and everything works, right? Your PowerPoint will now fail in like strange ways, so they have to know how to deal with all these little issues. They have to keep track of all these threads. They have to know what's going on with the threads. If any thread does something wrong, they have to react to those stuff, and that's not trivial. So if you remember computing from around 99 to 2000, like till now sort of thing, not all applications would be multi-threaded immediately, right? Of course, they don't advertise it on the box, right? They don't put it on the box. We are fully multi-threaded. You can go as many processes as you want. But you run into more problems. And some of you may remember, like in the early 2000s and stuff, if you had some problems, Microsoft will tell you, go to your machine, reboot it with just one processor, right? And magically it'll fix all the problems because of these issues, right? It's not a trivial thing, but the hard part is, if you don't go through all this complicated stuff, you cannot leverage the newer machines which are coming out, right? So as a software developer, you have no choice but to use threads, but threads are not as easy as you would imagine, right? The good thing about threads is a thread, you can create a thread very easily, and that thread can do whatever it wants within the application, right? Which, as a OS developer, it rings a bell. So you go like, yes, it's good that it can do whatever it wants, but what if it does something that I don't want it to do? Then how do you debug? How do you manage these things, right? And I haven't even talked about how you would debug these things, right? Debugging a threaded program is very hard, right? So I think very few of you said you know how to debug, right? How many of you know how to debug a program? So how do you debug a program?
GDB or Valgrind.
So like what is your algorithm for debugging? What do you do?
I usually assign breakpoints to where I want to look at each possible problem, and then I'll walk through the call stack.
Yeah, so for people who don't use debuggers, right? The traditional way you debug your program is if you suspect that, like, let's say line number 10 is causing some trouble, you set a breakpoint, right? Which essentially means that your program will run fine till it comes to line 10 and it'll stop. And then it gives you control. So you can look at the variable values. You can look at what's going on with the program. You can single step. You can essentially go one line after the other. And then you can let it go, right? But the main thing you want is you want to be able to stop at line 10 and have control to you as a human being so you can examine the state and do stuff, right? So imagine what happens when you have multi-threaded program, right? Suppose you have like 10 threads, right? So what does it mean to say, I want it to stop at line 10, right? You no longer say, I want it to stop at line 10. You want to say, I want it to be stopped when thread 4 comes to line 10. Right? Because all of them are going independently. So you want to say, when this thread comes and stops here, I want the program to be stopped. Fair enough. It's easy to do, right? But the problem is, once you stop this thread, what are the other threads supposed to do? Are they supposed to keep going, or are they supposed to all stop, right? And either way, it's problematic. If you say they should go ahead, then you may not see what problem you were seeing before because the other threads are going full speed. If you want them to stop, you cannot know where the other threads are because they are all independently moving around. So they could be, when you done it first time, they could be in line 1, second time line 5, third time line 10, right? So debugging those becomes much more complicated because you have to deal with the stuff that the timing matters. All of them are going through. You want to make sure that you don't want them to be lockstep. You don't want them to be going at lockstep because then the whole thing is not that interesting. But if they're all going whichever way they want, right, how do you kind of figure out what's going on with one thread when all the other threads are going around, right? So can you imagine like what's the kind of chaos you have when all the threads are going around? You ask one thread, you say, what are you doing? And by the time you ask the stuff, the whole system is finished and what have you, right? So it's not, so you can in GDB you can say, I want, when that thread goes to what line, I want it to stop. But that's not exactly that easy when you do it in practice, right?
The Visual Studio 2008 debugger is actually thread aware, so you can pause it at different times and stuff.
Yeah, so the thread aware ones know about threads, but it's still complicated to see. So you have 10 independent things going on at the same time, right? So for you to know exactly if you think of this as like, if you, there are 10 things going on, right? At the best, the debugger can tell you what's going on with all 10 of them. But if you want to look at it on the screen, right, you have 10 different things going on at the same time, right? If it's one, it's sort of easier for you to look at and go like, yeah, this variable is going up or going down kind of stuff. And now you're looking at 10 of them. And the fun comes in when you want to see them interact with each other, right? So one of them is adding, one of them is subtracting. And you're trying to grasp this fashion that there's 10 of them, they're all doing what they want to do. To me, it's like a daycare facility with 10 kids running around, right? You're trying to see all of them. You want to make sure you know exactly what's going on with all of them. But all of them are doing something independently. So you can stop all of them and say, okay, now all of you take one step, now all of you take one step kind of stuff, which may work, but that's not the real way the programs are running and trying to do that, right? Yeah. So there's more support now, but it's still a lot more trickier than single process, right? And especially when you have like complicated programs like PowerPoint. So I think one of you mentioned last time, you would like in PowerPoint one thread to be doing spell checking, one thread to be doing grammar checking. They're all operating on the same data, right? If one of them causes some failure, there's so much data in each one of those stuff, it becomes very hard to debug. The other notion is the notion of thread pools. This is a notion that web servers and all work on, where you don't want to ask the kernel for new thread all the time because you're a web server. You know what you're going to do. You know what is the status. So you create this notion of a thread pool where you create, let's say, 10 threads before you start your program. You initialize all those stuff, and they basically wait for work, right? So when you get a new web request, you put it into this thread pool. You put it into a shared data structure, and one of these threads will take it and do whatever it has to do and finish it, right? So the idea here is I don't want to create threads as needed. I create a certain number of threads, and the job of each thread is to go do what it has to do, like service one of the customers, and then it'll wait for the next job to come back into the threads, right? It's a nice paradigm. It's used heavily in most of the web servers, right? The nice thing is you can control how many threads you want. So if you look at the Apache or whatever, it'll tell you how many threads you want to allocate, and depending on your system, you can have that many threads. The bad part is now you have to worry about what they can share, what they don't want to share, right? So you don't want different applications to share something. So you may have to have a notion of a thread-specific data, which is one of the things you want, right? You can say I'm going to create 10 threads in the thread pool. Each of the threads will have its own data, which other threads cannot see, just so that I can have a notion of web servers servicing different content. So one of the threads can be giving your grades, one of them can be giving your grades. You don't want them to have access to the other data, but it still operates like a thread, right? You still get the performance of threads, but the protection of a process where things don't get shared, right? The last stuff, we're not going to go through detail. This is one of the good research projects which came out of the stuff, which is the notion of, if you realize the notion of a system call, right? System call is a way for you as a user to call the operating system, right? But the important thing to remember is operating system does not, even though it is powerful, even though it is supervisor, it does not get control till you call me, right? So if I know you are a multi-threaded program, and I know that you are a user level thread package, and I know that you are managing, I gave you 2 threads, but you're giving it to 10 users, but I want to tell you something. Like for example, I want to say, I have one more thread, kernel thread, that is running free, right? I'm on an 8 processor machine. You only asked for 2. I could give you one more, right? Because I don't have any use for it. As operating system, I know this stuff. But I cannot give this to you unless you ask me, right? So the way you as a user library writer would have to do is keep asking me every time. Like, do you have extra spare thread that I can have, right? So the only interaction you have right now is, unless the application makes a system call and asks me stuff, I as operating system cannot tell you something. I cannot tell you you have more. You can have more threads. Or I cannot also say right now we don't have too many processes. So even though you ask for 2 kernel threads, I'm going to take away one of those, right? Until you give it away, I can't do anything, right? Which is a problem when you're trying to do this user level thread library, because either way, I cannot take away stuff from you, I cannot give it to you without you knowing about it. So the notion of a scheduler activation is the notion of an up call, right? Which is the inverse of system call. Up call would let the kernel call you, right? So up call is exactly like a system call, except you would say, you would register up call, you would say, if I'm going to manage threads. If anything happens with threads, let me know by calling this function, right? So it's like a system call, but the operating system will call you and run your program. So it can say, I'm going to take away one thread. So you can say, if you want to take away a thread, call this function. Or if you want to give me a thread, call this function. And that's a way for me to call into you and tell the application, even though the application did not call me. Does that make sense? System call is always one way, right? Till you call the system call, the operating system may know something else which will make you good, but it can't tell you till you ask me. Up call is a way for me to call you and tell you, right? Of course, there's issues of safety and all those things, because I don't want you to tell me something where I shouldn't go, because I'm still a supervisor. So the challenge is to make sure that we do it right, such that I can make this up call to you, so I can give you the information I have that will make you run a better thread library without having to violate security and all those things, right? So without the notion of up calls in traditional operating system can never tell you anything. It can send you signals or what have you, but it cannot tell you something proactively till you do something, right? And you'll realize that once you think about it, it's a limitation. It has to be there because of protection issues, but it's still a limitation, right? You cannot say right now I have too much resources. Please have some more. I cannot say, I don't have any resources, I want to take it away from you. But I'm going to give you a chance, right? I'm going to give you a chance that I'm going to take it away, but you can respond to it, you can adapt to it nicely. Right now, all you can do is you can just take it away, and then you kind of figure out what's happening, right? And so this is a very powerful mechanism, and most operating systems tend to implement those, right? So the next few slides is the notion of how the different operating systems deal with those stuff. Windows XP has a one-to-one model, right? So you can have your kernel thread mapped directly to the user level thread. You can also write a pthreads library or so, which can do the application level modifications. And it has a few some other data structures to keep the different kinds of threads. So in Linux, right? Linux does not have a notion actually of process, right? Linux, everything is a kernel level thread, right? What they call tasks. So Linux is a kind of hybrid, which is more closer to kernel level thread than a process. And depending on how you manage the memory mapping, it acts like a process or it acts like a kernel thread. But essentially, according to kernel, there's only one concept. It does not know the concept of process and a thread. It knows about a thing called task, which is much lighter than process, much more heavier than a thread. Right? You'll see later on how you create the notion of a process by having this notion of pages and stuff. But essentially, all it knows is a task. And depending on what pages, what memory gets assigned to you, you look like a process, right? So for example, if it creates two tasks, if both of them don't share the same object, same pages, then they are processes, right? Because processes don't share something. If within the kernel, if it tries to make them share stuff, then it behaves like a thread. But within the kernel, there's only one concept, which is a kernel level thread, right? And then the last one is the notion of a Java. Java knows threads all the time, and you use them using the extend thread class and implementing a runnable interface, right?